Here's an example of a hypothesis tree applied to an engineering problem. I'm going to use the example of a porous burner. These are essentially, this is a porous ceramic in some sort of duct into which you add a fuel and an oxidizer, and you get some flame inside. The advantage of these types of flames is that they can burn at lower temperatures and produce fewer pollutants in your exhaust stream. Anyway, without going into any more detail, the hypothesis is a precise statement. So we might have decided to use a porous burner, or to investigate using a porous burner in some application. So we're going to make the hypothesis the fuels can be burned in a porous burner. It's a precise statement. Now we need to think about everything that has to be true for that to be true. So to start off with, we'd say the velocities in the burner will not extinguish the flame. In other words, we won't be introducing the fuel and the oxidizer so quickly that they blow the flame out. And for that to be true, the required flow speed needs to be low enough, and the flame speed needs to be high enough. Now what we have here, we'll know what the flow speed is. It'll be set by the conditions of our burner, or at least we'll be able to change it. We'll have some margin on how we can change it, so we'll have some sort of idea of what the flow speed is. And now we can do a very targeted analysis over here to calculate the flame speed at different mixture ratios, and with those two combined bits of information we will be able to tick or cross this hypothesis, the first one. And we do this again and again. So for example, the second one would be that the flow can be sufficiently pre-mixed without auto-ignition. What that means is that when we mix the fuel and oxidizer upstream, they don't spontaneously burst into flame before they hit the porous ceramic. And again, now we get a bunch of, when we divide this hypothesis up, we get a bunch of other things that we can test. The auto-ignition time is large enough. Well, we can take a particular mixture ratio and work out that auto-ignition time. That is the time it takes before the fuel and the oxidizer spontaneously combust. And secondly, we need to be able to mix the flow well. Now, we might have some geometric constraints on the size of our burner. So the third hypothesis is that the required surface area is small enough to fit into our burner. And again, we can divide this up into various hypotheses. And finally, you'd say the pressure drop is sufficiently low for our application. Well, you can test that quite simply by having designed your burner to just see what the pressure loss is. Is it big enough or small enough to prove or disprove that hypothesis? So the point is, we've started off then with a precise statement. We've divided it up into 1, 2, 3 and 4, which again are precise statements, each of which has to be true for the primary hypothesis to be true. We divided these up into smaller statements as well, but these can be tested with some sort of analysis that we can do relatively easily. And you can see you can do all of the analysis on the right, and having done that, you can be fairly sure whether you can tick or cross that primary hypothesis.